In this recording, we're going to analyze how a low-pass filter responds specifically to cosine inputs. I've drawn our RC filter over here, and I've drawn a little cosine at the input just to remind you that we're going to be putting cosines into it today instead of step functions. I also want to take a moment to do a little bit of an analogy. I want you to imagine a bucket that we're trying to fill with water. In this case, the bucket is essentially our capacitor that we're trying to fill up, and the faucet is essentially represented by the resistor. So the bigger the resistor, that's more resistance to the flow of water. So a big resistor means less water that's going to flow into the bucket. So what I want you to imagine is that if this is going cyclically, if current is flowing in and out, then if we have a slower frequency, right? So if the bucket fills and then empties, and then fills and then empties, that means it's going to have more time to fill. Okay, and then it's going to have more time to empty. So that means that if it's slower, that means the capacitor is going to, the bucket is going to have a better fill. Okay, it's going to have a more complete fill. If we increase the frequency, if we fill and empty, fill and empty, fill and empty really, really fast, and the bucket never has a chance to fill up. So that means it's going to have less fill, and that's a nice clean way of thinking about what a low-pass filter is. Better fill is essentially saying like the capacitor is going to take on more charge, so it's going to be passing the frequency better. So this is a nice way of thinking about a low-pass filter. Another reason why this example is instructive is if you imagine now what happens when you make the capacitor bigger. What happens when you make the bucket bigger? If you make the bucket bigger, in other words, if you have a larger capacitor, the bucket gets harder to fill. Okay, so harder to fill, meaning that it's going to require slower frequencies to fill. So it's going to need lower frequencies to fill. And the same thing would happen if you had a larger resistor. If you had a larger resistor, that would mean less flow of water, less flow of current, and that would also make the bucket harder to fill, which means it would need a lower frequency in order to fill it. And that shouldn't surprise us. We learned in the previous video that if you make either R larger or the capacitance larger, that means you have a larger time constant and a lower cutoff frequency. Okay, so if you make either the resistor or the capacitor larger, then that means that only the lowest of the low frequencies now are going to be able to properly charge and discharge your capacitor. Anyway, so that's a little bit of a physical example that can help some people visualize what's going on with the RC circuit. Now, let's try to find mathematically a way to imagine what happens when we put a cosine into the circuit. So here's our differential equation, and that's the same one we have from the last video. And all I'm going to do here is just rearrange the terms. And in theory, then for any input voltage, I should be able to say, suppose my input voltage is cosine of omega t, then I should be able to do a whole lot of math to solve that differential equation and get V out. But that math that's hard math. And not that we can't do hard math, it's just that there's an easier way, and we should certainly exploit that easier way if we can. So the way we're going to exploit the easier method of doing this is we're going to use the Fourier transform. And we learned in an earlier video that when you take the derivative of a signal in the Fourier space, if you take its time derivative, then in the Fourier space you essentially just multiply it by j omega. So let's try that and see what happens in this case. Let me just rewrite the differential equation over here just so I have a little more space. So rewriting this down here, we have dV out dt plus V out over RC equals V in over RC. Okay, and that's all with respect to time. Now we'll take the Fourier transform and convert it all with respect to frequency. So the derivative of V out becomes j omega times V out as a function of frequency plus 1 over RC times V out as a function of frequency equals 1 over RC times V in as a function of frequency. And now I've essentially linearized my equation. So I can collect like terms on the left and say V out times j omega plus 1 over RC equals V in times 1 over RC. And finally I can say V out equals 1 over RC all over j omega plus 1 over RC times V in. Or if I really want to tidy it up, I can rewrite that as 1 over j omega RC plus 1 times V in. So what on earth does that mean? Let's actually use some numbers here. So let's suppose that our input voltage is a cosine at, let's say, 100 hertz. So V in equals cosine of 2 pi times 100 hertz t. And if I express that in my complex notation, it's going to be a e to the j omega t plus a conjugate e to the minus j omega t. And essentially, if I express it in that form, I know that omega is equal to 2 pi 100, and a is going to equal k over 2, so it should be 1/2 e to the j theta. And sorry, and theta in this case is 0. There's no phase shift. So 1/2 e to the j 0. Okay? Now, this term here, we're going to call the transfer function. We're going to call that h of j omega. That's the transfer function. And let's evaluate it. So in this particular case, the transfer function, h, is going to equal 1 over j omega, and in this case our omega we agreed upon was 2 pi 100, times r, which we said, we didn't give values of r yet. So let's let our resistor be a kilo ohm and our capacitor be a microfarad. So that's going to give us 1,000. So j omega r c, c is 1e minus, what is it, 6, plus 1. Okay, now this is a complex number. You go ahead and you type that into your calculator, and I'm going to get my result back in polar form. I'm assuming everybody can work the math at this point. If you calculate this number and get the result back in polar form, you get the following. You get 0.85 e to the minus j, and I'm going to be a little bit unprofessional and leave my phase angle in radians, e to the minus 32 degrees. I could put it in, sorry, I'm going to put my phase angle in degrees, not in radians. Okay, so finally, according to our equation before, V out is going to equal h times V in, which is going to equal 0.85 e to the minus j 32 degrees times our value of a, which was 1/2 e to the j 0. And when I put it together, what I've got is 0.85 over 2, which is 0.425 e to the minus j 32 degrees. And what I have now is, this is the A value for my output. And since nothing else changed, since nothing affected the frequency of my signal, my output is still going to be a cosine at the same frequency. So to put it all together, I can say that my output voltage, V out as a function of time, is going to equal 2 times the absolute value of 2 times the absolute value of A, which is 0.85 cosine 2 pi times 100t minus 32 degrees. Okay? And there you have it. So, here's what I want you to get out of this video. First things first, when you put a cosine in, you get a cosine out. And the cosine that you get out is at the same frequency. Okay, when we did this analysis, nothing here altered the frequency. There was no adding or subtracting of anything to the value of omega. Okay, so the first rule of linear systems is that cosine in gives you cosine out at the same frequency. That doesn't change. Okay, we had 100 hertz in, we get 100 hertz out. The only thing that gets changed is the amplitude and the phase. And the amplitude and the phase get determined by the transfer function. And the transfer function got determined in turn by taking the Fourier transform of the differential equation. Now, a final thought. If we go to MATLAB, we can actually plot the transfer function, 1 over j omega RC plus 1. We can plot its magnitude and we can plot its phase. So if we come over here to MATLAB, you can see that I've already typed in all the code. I'm going to define a 1000 ohm resistor and a microfarad capacitor. I'm going to define the frequency vector. Instead of lin space, I use log space. That's going to give me log spaced frequencies from 10 to the 0 to 10 to the 5 in this case. And then equals 2 pi f. That converts it into into radians per second, excuse me. And then here's my definition of h, 1 over j omega RC plus 1. So that will give me complex values for h, and then I'm going to plot their, for now I'm just going to worry about plotting their magnitude. So if we go ahead and run this, you can see that in figure 1 I just used the plot command. I'm plotting the magnitude of h, and essentially what you can see is that we have a bit of a low pass filter going on. Low frequencies get passed with a gain of 1, and then high frequencies get rejected. Now what you'll notice is that while technically true, this plot is really hard to read, and the reason is that it's hard to see what's happening at low frequencies and at high frequencies at the same time. So instead, I'm going to use the semilog x command, which is just another way of creating a plot instead of using the plot command. But the semilog x command forces a log spacing on the x-axis. So this is the exact same data, it's just with a log spacing on the x-axis. And now you can see nice and cleanly that I have a low-pass filter. At low frequencies, I have a gain of 1. At high frequencies, I have a gain of 0. And you can tell roughly by eyeballing it where we transition from passing low frequencies to rejecting high frequencies.